Hey guys, today we are going to be looking at how to calculate a confidence interval for a single mean. So that means that I'm going to be presenting numerical data to you this time, and you'll be creating a confidence interval using numerical data. What you're going to need for this confidence interval for a single mean is you're going to need the mean or the average and the standard deviation. So there's two different ways that I can present the data to you. The first way is if I give you something called stats. So stats means I give you directly what the values are for the average or the mean. So you might see it presented as an average, but just know that that actually means that x with the bar over it, so that is your mean, with a standard deviation of 3.2. Or I can give you the notation where the Sx equals 3.2. So that's if I give you the stats directly. Another way that I can present the data to you is if I give you the raw data. So the raw data means that I give you the list of values, meaning like if you're taking let's say you take a test with 20 questions and this is the amount of questions that each person got right. So this is a list of raw data. From the raw data, you're going to have to calculate your mean and your standard deviation. So that either be using a calculator, using the stat edit, one var stats that we've been using so frequently with a TI-84, or you can use a basic, I think TI-30 plus or something. So stat edit, and you're going to one var stats. And if you don't have a calculator like that, then you can just Google like a website that can give you the standard deviation and the mean. So if you click on the PowerPoint that I presented with the empty notes, you'll be able to access this link. I think this is a pretty decent website that gives you the mean and the standard deviation. Okay, so a confidence interval for a true single mean, you're going to be given one data set. That's important because eventually we're going to actually look at giving two data sets. So for this formula, you're only given one data set. There are a few conditions for a confidence interval that have to be satisfied. You should see data that's normally distributed, so it's roughly symmetric, unimodal, and bell-shaped. So it does have that, symmetric idea to the data. We don't want any skewedness because remember last unit we don't want to use the mean when we're dealing with skewed data. And then we also want to have a random sample. So the sample that we get should be randomized. It shouldn't be something that can contain bias. So when we're looking at the actual formula, so for a 95% confidence interval, you've got this x bar plus or minus 2 times s over the square root of n. So let's just talk about what each one of those means. So the x bar represents your sample mean. So it's not the population mean because that's what you're trying to estimate with a confidence interval. So this is your sample mean. Okay. And then this is your sample standard deviation. So sample standard deviation. So we're trying to estimate a parameter or a population mean using samples. That's why we want data that's normally distributed and random. The last thing is this n. This n represents how many numbers you have or how much data you have. So how many total observations. Okay, and again, that 2 comes from the 95% from the empirical rule where 2 standard deviations is 90, below and above your mean is 95% of your data. So there are some ways that you can make a confidence interval smaller and more accurate. If you look at a smaller standard deviation, so if you're dividing like a smaller number on the top versus let's just say the sample is 16 numbers versus a larger number on the top. The smaller number is going to create a smaller margin of error because it's going to be a smaller fraction. So a more consistent athlete or someone who has data that's closer together is going to have a smaller, more narrow confidence interval. And then there's another way that we can make our confidence interval more narrow and just more accurate is by looking at a larger sample size. So again, if we want a larger sample size, the standard deviation is going to be smaller if we have, 200 as a sample, or not the standard deviation, the fraction will be smaller if we have a sample of 200 versus a sample of 10. So this number would create a smaller margin of error. And again, for the same reasons, it would then create a smaller, more narrow confidence interval. Okay, so here's the first type of example that I can give you. See if you can recognize if it's stats versus if it's raw data. So in 36 games in the 2007 to 2008 regular season, the observed standard deviation of LeBron's performance was typically 8.04 points away from the true mean of points, with an average of 30 points per game. So this is an example where I give you the stats. So I give you exactly what the mean and what the standard deviation are. Okay, there's a few numbers that we have to pick out in order to calculate our confidence intervals. So we need the sample mean, we need the sample standard deviation, and then we also need how many total numbers we're looking at, how many points he's making per game. So I'm reading in here, I've got 36 games. So that 36 is going to represent my n. Keep going, the observed standard deviation was typically 8.04. So 8.04 is my standard deviation. Away from the true mean, that's what I'm trying to estimate using the confidence interval. And his average, the sample mean was 30 points per game. Okay, from here, we're ready to just kind of plug in to the formula. So we have the mean, which was 30 plus or minus 2, which comes from the 95% from the empirical rule, times the standard deviation, which is 8.04, all over the square root of 36. So I always advise you to get those numbers broken down within the parentheses first before actually multiplying by your multiplier. So 30 plus or minus 2 times 1.34, and that ends up being 30 plus or minus 2.68. So in this case, we talked about this with the single proportion, but I don't think I've talked about it yet for this one. The x bar for a single mean, that's going to be my single value estimate of this formula. And this plus or minus 2 times s over the square root of n, that's going to be my margin of error. So in this case down here, 30 is my single value estimate. That's how many points I think he can score per game looking at, an infinite sample size. And then this 2.68, that represents my margin of error. So that's how much I think he's going to be within, or my true mean is somewhere within that single value estimate by 2.68 points. So go ahead and subtracting and adding out those values to get your confidence interval. So that's just your single value estimate plus or minus the margin of error. That's not the confidence interval. So if we subtracted, we would find that the confidence interval, he scored on average from 27.32 to 32.68. So his true mean is somewhere within there with 95% confidence. If we're interpreting it, we always start the same way. So we are 95% confident that the interval of plausible values of from 27.32 to 32.68 contains LeBron's true mean to score points per game. I can even go ahead and say in the 2007 to 2009 or 2008 season. Okay, and here's another example for you. So in the 2008 season, Jerome Bettis of the Pittsburgh Steelers, he is my favorite Steelers player, by the way. He led the NFL in rushing yards. Here is rushing yard totals for each game. Just a side story, he used to live in Roswell, and he used to get full-size candy bars for Halloween. So that just obviously means he's a model person. The best. All right. So in this case, I am giving you raw data, which means I'm listing out all the values. You're going to have to calculate the mean and the standard deviation from the list. So I went ahead and I opened the website that we used. Let's see, it might be a little messed up, but this is kind of what that calculator looks like. Okay, I entered in the data already in a list. This is from a sample, and then you press calculate. Oh, great. Okay, so maybe it wants us to separate by commas. No problem, just gonna take 45 minutes here. Anyway, hope you guys are all doing good. Hope you're surviving the pollen. Almost done. Bear with me. Okay. All right. So it gives us how many total values I had. So I had 14 total values. The mean with our X bar is 103.87. And then if you scroll down the page, it shows you all the calculations for variance and your standard deviations down at the bottom, 50.503. But what I noticed that was something kind of cool is it actually already gives you your margin of error. And if you keep going further down, it gives you the confidence level for different percentage of confidence. So it's kind of cool. It shows you how big that confidence interval can get and how you can be, even though your percentage of confidence is going up, your interval is going up because you're expanding the width, which makes more numbers capable of being that true mean. So it's kind of like does the work for you almost. But I'll show you the formula here back at the PowerPoint. Okay, so from those values, it told us that the mean was equal to 103.86. Okay, the standard deviation is 50.5, and it told us that our n was 14, so there's 14 total numbers here. Okay, so I have 103.86 plus or minus 2 from the 95% confidence of the empirical rule times 50.5 over the square root of 14. Okay, 103.86 plus or minus 2, and that's going to be, I think I went ahead and just multiplied it out, so plus or minus 26.99. Okay, that means that I have my single value estimate is 103. That's what I think his true mean is, so that's my single value estimate. My margin of error, if you add and subtract it out, you're going to end up getting a bracket, so an interval from 76.87 to 130.85. Okay, so his true mean of rushing yards for each game is somewhere between these two values. So for interpreting it, we are 95% confident that the interval of plausible values from 76.87 to 130.85 contains Bettis's true mean of rushing yards. That says true. Okay, so the last thing I want to talk about, which is going to be a lot of different questions that you're going to see on your quiz tomorrow. Okay, it says, are you convinced that Jerome Bettis could have a true mean of 90? If he has a true mean of 90, what we're doing is we're taking our interval and looking inside to see if that's in there. Could he have that value? Is that value located in your interval? And we're going to say yes, because 90 is contained in the interval. Or 90 is within the interval. Now, he couldn't necessarily have a true mean of 60, or he couldn't have a true mean of 140 because that's not in your interval.